Hello everyone, welcome to the journey into the quantum mechanics. And with this presentation, we'll cover the principles of quantum mechanics, which will governs the state of the behavior of the atoms or particles in quantum realm. And these principles of quantum mechanics includes, we will cover uh, why the known mechanics, quantum mechanics is defined, established. So that limitations of classical mechanics. So we try to justify that with limitations of classical mechanics. And the fundamental step for quantum mechanics, which is de-Broglie hypothesis of matter waves. And accordingly, the Davison and Germer's experiment, which proves the wave nature of matter. And then mathematical tool, which is Schrodinger's time-independent wave equation. And we'll see two applications of the Schrodinger's time-independent wave equation to solve the physical problems. So that two physical problems here we'll cover, that a particle is trapped in one-dimensional potential well, and the second physical problem, which is tunneling effect. So these are the concepts. These are the concepts we will cover through this video. Now I'll go to the limitations of classical mechanics. Here we are saying that as limitations because the listed concepts are not able to justify, are not able to explain by the classical mechanics principle. So the list, a number of physical phenomena are there. Out of that, I just listed five physical phenomena. For example, I just took five examples. These phenomena are not able to explain by classical mechanics, and they are the stability of an atom and the photoelectric effect, black body radiation, Compton scattering, and emission of alpha particle from nucleus. So we'll give a little in detail explanation for this one by one. How the classical mechanics is not able to explain the phenomena and how that successfully explain the phenomena by quantum mechanics. So out of that, the first one is stability of an atom. So classical mechanics saying that if any particle or object moving continuously, if the particle is moving continuously, its kinetic energy will gradually decreases, and finally at a particular time the kinetic energy will reach to zero. So if you apply that principle, if you apply the concept from this classical mechanics to the electron moving around the nucleus, mostly electron is revolving around the nucleus. So in this, electron is moving continuously. So if we apply classical mechanics, that electron should decrease its energy gradually, and finally, after some time, that electron should reach to the proton. So after some time, there will be no concept of electron because as per classical mechanics, it will reach to the nucleus after some time. So it shows, if electron is reaching to the nucleus, if it is finally fall into the nucleus, there is, any matter is not stable. Matter is not stable. But practically, if we see, the matter is matter is looking to be stable, right? So this, this principle, this the idea of classical mechanics is failure. How that matter is still stable. But this is explained by later on by applying quantum mechanics principle that electron is revolving around the nucleus, of course, but that electron is exhibiting a wave nature. It's not like a straight line path, it is exhibiting a wave nature. And more strictly, the type of wave is a standing wave. And the characteristic property of standing wave is the energy will not come out from the system. That energy will be within the system only. right? I mean, here that system is a nucleus and around that electron. So as long as that electron is moving in a particular orbit, and I mean, that's why we will say that orbits are as stationary orbits, stationary orbits. So as long as that electron is revolving around the nucleus in stationary orbits, that electron will not radiate energy, or it will not absorb the energy until and unless we are not disturbing. So it will maintain this energy constantly throughout the motion. So that's why you can say if that energy is constant, we can say that atom is stable. So here the idea from quantum mechanics is electron is exhibiting the wave nature. This idea is able to successfully able to explain the stability of an atom. I mean, of course, this idea is a part of what quantum mechanics. And the second example, which is a photoelectric effect. Photoelectric effect. So first we'll try to understand little briefly what does it mean by that. So if any metal surface is encountered by a photon, then electron will be ejected from the metal surface. Electron will be ejected from the metal surface. But one crucial word is missing as per until now. Of course, the photon should incident on the metal surface. Photon of suitable frequency. You can say suitable frequency, or in another way suitable wavelength, or in another way suitable energy. You can define with any of these three terms. So ejection of electron from the metal surface, if it is illuminated with a photon of suitable frequency, is photoelectric effect. Classical mechanics is saying that if the light is having sufficient intensity, if that light is having sufficient intensity in the sense number of photons per unit area, right? If that light is having sufficient intensity and there is no dependency of frequency or energy or wavelength, whatever, I mean, any frequency of light or any wavelength of light can exhibit the photoelectric effect. So classical mechanics is saying that it depends on only the intensity of the light, but there is no dependency of frequency or wavelength or energy of light. But practically, if we observe, I mean, experimental results saying that metal surface is responding to the light not for all the frequencies of light, only certain frequencies of light only the metal surface is responding. So, I mean, quantum mechanics is introduced to this word, suitable frequency, not for all frequencies of light, only certain. So, this is the idea of quantum mechanics. The electron could be emitted only if that light is suitable. Suitable in the sense, just here, that depends on the type of metal surface we are using. Here, I just given some examples. If it is sodium, the suitable frequency is 5.52 into 10 to the power of 14 hertz. And for magnesium, it is 8.90 into 10 to the power of 14 hertz. For calcium, it is 694 into 10 to 6.94 into 6.94 into 10 to the power of 14 hertz. See, these are the suitable frequencies for these metals. And if you see, even you can observe in this G file. Now let me, this is potassium metal surface. Now that light wavelength of red color, I mean around 7,000 angstrom, around 7,000 angstrom is illuminated onto the metal surface. There is no ejection of electrons. See, you can compare with this diagram, yellow color wavelength light. So now this potassium surface is not responding to this wavelength, right? and the same potassium surface is starts responding for a wavelength of yellow color around 6000 angstrom, around 6000 angstrom. See, now that electrons are coming onto the surface, now like this is suitable frequency. If it is integral of the suitable frequency, I mean, see this blue color. For blue color, I mean around 4000 angstrom, around 4000 angstrom, and that electrons are ejected, coming onto the surface, and they are ejected. I mean they are moving out of the metal surface. Right. So here the suitable frequencies for potassium, suitable wavelength for potassium is 6000 angstrom. So that depends on the metal we are choosing. So the conclusion, the metal surface will respond to not respond to all the frequencies of light, only certain frequencies of light. I mean suitable frequency. Suitable is that depends on the type of metal. And the third phenomena, which is a black body radiation. Uh, Black body radiation, I mean, it is an ideal source. Generally, it is an ideal source. I mean, it will absorb the energy. If it is absorbing some amount of energy, the same amount of energy will again, it can radiate. Of course, it is an ideal case. But if you see both the mechanics principle, I mean, classical mechanics is saying that if you I mean, the radiation emitted from the black body will be infinite at lower frequencies. When at ultraviolet region, say you can observe here. This is this graph for as per classical mechanics principle. So you'll say that at lower frequencies that intensity of light will be infinite, and we'll say that is ultraviolet catastrophe. But experimental results is showing that not like this. So classical mechanics is unable to explain that. Experimental results is showing the second graph. I mean, at lower frequencies, intensity of light will be less, and even at higher frequencies, also low intensity of light will be less, and uh, the more response when the frequency is moderate. Right, so there is no ultraviolet catastrophe practically. So I mean, light emitted from black body radiation, and this theory, I mean, this quantum mechanics theory is based on Planck's theory of radiation. Planck's theory of radiation from quantum hypothesis. And number four, Compton scattering. Uh, Here, that Compton scattering is if light, I mean, any photon is incident and interacted with an object, like any object or particle, the direction or the position of the particle will changes. Here, let be this particle is electron. If that light is in collision with this electron, that electron will be recoiled. And here shows that particle nature of photon. Particle nature of photon, because after collision the direction of, I mean, the direction of electron is changed, and the incident photon, whatever it is, that will also change its direction by theta. So here this is the concept of quantum scattering. And classical mechanics theories, so after collision, I mean after scattering, there will be no change in wavelength, or you can say no change in frequency of this photon. I mean, this incident photon and scattered photon both is having same frequency, or you can say same wavelength. But practical results are showing that the frequency or wavelength is not coming to be same before and after collision. Right? But quantum mechanics principle is successfully explained that after collision, the frequency of the photon will definitely changes. Let be nu is the incident photon frequency, and this is in collision with the electron. So this is scattered electron, and this is scattered photon. Now the frequency of this scattered photon either nu plus or minus delta nu. So there may be a small increase in frequency or there may be small decrease in frequency. These are the practical results, and it is successfully explained by the quantum mechanics principles. Right, so all these are some of the examples which are not able to explain the classical mechanics, but how this is successfully explained by the quantum mechanics. Now we come in, enter into that, and the fundamental step for the quantum mechanics is de-Broglie hypothesis. De-Broglie hypothesis, or you can say dual nature of matter. First, this is a hypothesis because it is not having any practical proof at the time. Of course, later on it is proved, of course, but at the time of de Broglie is suggested, this concept is an hypothesis because he is not given any practical proof for this idea. And what is the basic? What is the strong idea behind this? Is this universe generally this universe is composed of two things. I mean, matter and energy. Matter and energy. So if you see the universe, anything will be in the form of matter or in the form of energy. And previously it is already proved that energy exhibits energy exhibits both particle nature as well as wave nature. Energy like light which consists of what? Photons. So these photons are exhibiting both particle nature as well as wave nature. So the idea is, of course, nature always try to maintain the symmetry. It means if energy is exhibiting both particle nature and wave nature, then why don't the matter? Why don't the matter? So matter should also exhibit both particle nature and wave nature. The particle nature of matter is already proved. So his new idea is the matter not only exhibits the particle nature but also exhibits the wave nature. So this is the crucial idea of de Broglie with this reference, right? So that's what I said. So wave particle duality, which earlierly it was applied to the light, but now as per de Broglie, this hypothesis can be applied for all material particles, all matter, right from subatomic particles like electrons to macroscopic objects also. But this wave nature for matter is predominantly exhibited by subatomic particles like electrons, small particles. I mean, you can observe that very predominantly in case of small particles. Right? I mean, macroscopic objects will also exhibit that, but that we cannot identify that much of easy. I mean, special instruments may be required. Right? And if the matter is exhibiting wave nature, then what is its wavelength? How much may be its wavelength? So the equation to calculate the wavelength of matter is also given by the de Broglie. And for this, it just took a simple idea. If matter is exhibiting both particle nature and wave nature, it just took the equation of energy of the matter, both in particle nature form and wave nature form. Simple idea. I mean, just here. So from Planck's hypothesis, energy of photon from quantum theory, it is E is equal to h nu. This is energy of the photon E is equal to h nu. And of course, where this h is Planck's constant with value 6.626 into 10 to the power of minus 34 joules. And nu is the frequency of that wave, I mean frequency of the photon. Now see this second relation for that same photon, but now you are applying the concept of special relativity. Special relativity, that is Einstein's energy momentum relation. The energy of the particle is related to its momentum. I mean that equation is E is equal to pc. I mean here both equations are energy of that photon, but here it is used the special relativity concept, and here it is used the quantum theory. Two different approaches, but both are equations for energy of the photon. So that's why if that is energy of the same photon, we'll make that equal. We'll make that equal. I mean this h nu is equal to what? Pc. I mean p is momentum and c is velocity of light. I mean velocity of photon. So equate if you equate with both equations one and two, I mean this h nu is equal to pc. And here you can write that instead of mu, you can write c by lambda. And if you replace that h instead of mu, c by lambda is equal to pc. On both sides c will be cancelled, so lambda is equal to h by p. So the wavelength of any matter is equal to h by p. But this equation till now we consider for a photon. If you are generalize that all the material particles, so the momentum of that particle is mp. Lambda is equal to h by mp. So this is the equation for wavelength of matter if it is exhibiting wave nature, and where this m is mass of the particle. What material particle we are choosing, its mass, and its velocity is v, and p is momentum of the particle, of course, which is product of mass and its velocity. Now we can write this equation not only in terms of momentum, we can write that in different forms also, in different forms of energy also. We'll see that in detail, all that equations. So the second one is of course wavelength of matter, but we'll write this in terms of kinetic energy. And we know already the basic equation for kinetic energy is half mv square. Right now we are trying to write this equation in terms of kinetic energy, and for that purpose we'll just multiply and divide with mass. Multiply and divide with mass right side, so that it will be m into m square v square and 2m. So that if you write this left side of the equation, 2m of k, which is m square v square. So that mv will be under root 2m k, 2m of kinetic energy. Now applying the basic source equation, lambda is equal to h by mv, and instead of momentum we can write under root 2m of kinetic energy. See, now the wavelength is in terms of momentum, the first equation. Now this is in terms of kinetic energy, the second equation. And we can write that equation in terms of electrical energy and thermal energy also. So for that, just we need to replace that kinetic energy. We replace that energy term in terms of electrical and in terms of thermal. So that kinetic energy of any particle in terms of its electrical energy is EV. E is charge of the electron, the charge of the particle. If it is charged particle, charge of the particle, and V is how much potential difference that we need to apply in order to gain its that kinetic energy. In order to move the charged particle, definitely potential difference is required. So how much it should be. So now the sequence. Lambda is h by mv in terms of momentum, and this is in terms of kinetic energy. Now instead of kinetic energy, you write this as EV. Right? If it is thermal in terms of thermal energy, now we need to define. How the particle can be moved by applying thermal energy. So the kinetic energy equation is Kinetic energy equation is 3 by 2 kT. So simply instead of kinetic energy, replace that kinetic energy with 3 by 2 kT. So final equation will be h by under root 3m of kT. So this is in terms of thermal energy. Now we'll see sample numerical problems on this all these equations. Now let me calculate de-Broglie wavelength for a charged particle like electron and proton. So the equation will be same, but the only difference is here we need to consider the mass of the electron. If it is proton, mass of the proton, and accordingly substitute all the corresponding values. I mean, h is Planck's constant, which is 6.626 into 10 to the power of minus 34 joule second, and E, charge of the electron or charge of the proton, both carries same amount of charge, so no problem. 1.6 into 10 to the power of minus 19 coulomb. And here the voltage, that potential difference, generally we will apply to move the particle. So we keep this P as it is. And the difference is mass of the electron is 9.1 into 10 to the power of minus 31 kg, but mass of the proton is 1.67 into 10 to the power of minus 27 kg. So if you substitute all these values, for electron it is coming to be 1.227 into 10 to the power of minus 9 meter, or you can say 1.227 by under root P nanometer. But for proton it is 2.866 into 10 to the power of minus 11 by under root V. But if you are interested to represent that value in angstrom, just the change the change will be 12.27 into 10 to the power of minus 10 by under root V. I mean, that is 12.27 by under root V angstrom. So the final result for electron it is 12.27 by under root V angstrom. For proton it is 0.2866 by under root V angstrom. And if you compare both the equations, apparently it is clear. Apparently it is clear. Uh, if the potential difference is same, we'll apply same potential difference for both electron and proton. Then the wavelength of electron is coming to be more. Wavelength of electron is coming to be more. And we'll see with different potential difference for both electron as well as proton. So we'll get some good analysis with these problems. So we already solved this both for electron and proton in this previous slide. But we'll apply the potential difference of 400 volt and 1600 volt. We'll see that for two different potential difference. If the potential if the potential difference is a 400 volt, the wavelength of electron will be 0.6135 angstrom. If it is accelerated by 1600 volt potential difference, 0.30675. And for proton, for 400 volt, it is 0.0143 angstrom. For 1600 volt, half of this, I mean 0.007, 0.0071 around angstrom. Now just see the analysis. For a same potential difference, we are applying same potential difference for electron and proton. But the difference is mass of the proton is more. So for this, the electron is exhibiting the larger wavelength. I mean, we are seeing the dependency of mass and de-Broglie. So the conclusion is lower the mass, larger will be the wavelength. Same way. Now, mass of the particle is same. Now we are analyzing for electron. Mass of the particle is same, but the kinetic energy is different. Of course, kinetic energy in terms of what the potential difference you are applying. And if you see, more the potential difference, I mean more the kinetic energy, lesser will be the wavelength. So these in this slide with these problems, just we analyzing the dependency of mass of the particle as well as dependency of the potential difference across the particle. And even we can calculate not only for charged particles, for uncharged particles also, like a neutron. Let be that neutron is having a kinetic energy of 128 mega electron volt. Right? So for that we need to choose proper equation. So this will be the suitable equation to calculate, because h by under root 2m EV is not suitable, because here the neutron is having not having any charge. The suitable equation will be h by under root 2m of k. So if we substitute the corresponding values, the Planck's constant as it is 6.626 into 10 to the power minus 34 joule second. Mass of the proton and mass of the neutron almost all same. So that's why we took 1.67 into 10 to the power minus 27 kg. And now it is accelerated with a kinetic energy of what 128 into 10 to the power of 6 electron volt. And if you simplify this equation by just calculating this, the final result is 2.533 into 10 to the power of minus 15 meter. So the conclusion is de-Broglie wavelength can be exhibited by whether it is a charged particle or uncharged particle. It's not an issue. It should be a matter. That's it. Charged particle like electrons and protons. Uncharged particle like neutrons is not dependent on charge. It is independent of charge, because both the particles are exhibiting the wave nature. I mean, this is non-zero value. I mean, the conclusion that we can give. So from all these calculation, we can conclude as the characteristics of matter waves. So here the mass dependency. The first point is mass dependency. So we already said lighter the particle, longer will be the wavelength associated with the matter. And the second point is the energy or kinetic energy, or you can say potential difference, or you can say velocity. So smaller the velocity of the particle, longer will be the wavelength associated with matter. Right? Let be. If the charge, if the particle velocity is zero, I mean that particle is at rest position, then what is the result? See this equation: h by m into 0. Something by 0 will be what? Infinite. So if particle is at rest position, lambda is infinite. What does it mean? Infinite, infinite in the sense we cannot define. We cannot define. So we cannot define wave nature for particles if they are at rest position. What does it mean? Only moving particles are associated with the wave nature. So we cannot adopt the concept of wave nature for rest particles. And the fourth point is it is independent of charge. If it is matter, then it will exhibit wave nature. So condition. I mean, till now this discussion, till from this discussion we can conclude, if any matter has to be exhibited wave nature, it should move. Its velocity should not be zero. Then only it will produce the wave nature, and it is independent of charge. Whether it is a charged particle or not, it's not an issue. And unlike some waves, they can travel through any medium. I mean, even they can travel with vacuum also. I mean, for example, if you see sound waves, they definitely require a medium. But unlike such mediums, they do not have. It doesn't depends on the type of medium it is propagating. Even it can propagate through vacuum also. And the last one, these matter waves will also exhibit the diffraction phenomena like other waves. And of course, the characteristics of wave, I mean the waves are characterized by if they are exhibiting the optical phenomena like interference interference, diffraction, and polarization. Diffraction and polarization. So these matter waves will also exhibit these optical phenomena, and this is our next concept. I mean, so till that de-Broglie time, it is just an hypothesis. And what that hypothesis is, matter exhibits particle nature, of course. Along with that, it will also exhibits the wave nature. He didn't give any proof, but later on, both these scientists, Davison and Germer, given the experimental verification for wave nature of matter. I mean, that is the significance of this experiment to prove the wave nature of matter. But which principle they use to prove that? The principle of diffraction. By using the principle of diffraction, they able to prove the wave nature of matter. So we'll see a little bit in detail. So first, what does it mean by that phenomenon? I mean, diffraction or diffraction. But it's I prefer to say diffraction because I will split that into like diff plus fraction. I'll try to justify this. I mean, the basic definition of diffraction is the phenomena of bending or spreading, of wave if they pass through if they pass around an obstacle or, or through any narrow openings. So you can visualize diagrammatically here. So these are the waves and they are passing through a narrow openings so that the direction of light is changed when the light is bent, or you can say that light is spreaded. And of course, it is not mandatory that if light is passing through any obstacle, it should exhibit that diffraction phenomena. So to exhibit that diffraction phenomena, one condition is there, that wavelength of that wave, that lambda, must be comparable with the size of this slit, size of this narrow opening. And this lambda must be comparable with size of the opening. Then only it will exhibit the diffraction phenomena. So what is happening here? I mean, what is happening? We'll try to explain that. A little bit in detail. Let be 100 photons. I'm just taking the random value. 100 photons are passing through small openings. If these small openings are not there, let be in the absence of these small openings, all the photons will follow the same direction. I mean, they will follow the rectilinear path. I mean, this will be the direction. All the photons will not change. They will follow the rectilinear path. But whenever this obstacle is placed, now all these 100 photons are spreaded to some region. I mean, I'm just taking the random values. Let be, I mean, because of this obstacle, let be 50 photons are not changing their direction. They're following the rectilinear path. And in remaining 50, 10 photons are changing their direction with some angle theta on both sides. On both sides. 10 on right side and 10 on left side. And some of the photons, I mean, let be five. Five photons are also changing their direction, but with some little bit larger angle. Theta, I will say theta 2 on both sides. See now that photons are spreading in a region, and then next some three photons are changed with an angle of theta 3. and two photons are changed their direction with an angle of theta 4 and so on. Now see there. Now all these 100 photons are splitted into different, all the photons are splitting into different fractions, different fractions. So here this diff fraction, right? The intensity is splitted into different fractions, is a diffraction. Now we are using this phenomena. I mean the Davison and Germer used this phenomena to prove the wave nature of matter. In what way? So if we observe the previous explanation, for any diffraction experiment, three primary components are there. The one is source, I mean, which will generate that wave, and the second one is grating, I mean, which consists of a large number of openings, large number of slits. And after diffraction from the grating, we need to collect all the diffracted wave, either by the screen, or you can get that either or by collector. So these are the common for any diffraction. But if it is specifically for the Davisson and Germer experiment, the electron gun is used as the source, and nickel crystal is used as the grating, and Faraday cylinder is used to collect the diffracted electrons. But here the question, I mean, how the nickel crystal can be used as a grating? That I'll try to justify it. So generally, grating is a device which consists of what? Which consists of equally spaced, large number of slits, large number of slits, and the device is grating. So we should found such a large number of slits in very small region, equally spaced slits in small region. We should found in nickel crystal also. Then we can use that as a grating. But is it possible to get this large number of slits? Definitely. So basic definition of crystal is regular and periodic arrangement of atoms. So I'm choosing one of these previous lattices randomly. All these dots are nickel atoms. All these atoms are, all these dots are nickel atoms. And now uh, the distance between any two consecutive atom is A, and it is equal everywhere. That is mean by regularity, regular arrangement. Distance between any two consecutive atoms is A, lattice parameter. And generally, the distance between any two consecutive atoms is the order of angstrom. Order of angstrom. I mean 10 to the power of minus 8 centimeter. Right now, just do a small calculation. If distance between two consecutive atoms is 10 to the power of minus 8 centimeter, then how many number of atoms will be there in 1 centimeter? So it will be simply a reciprocal of 1 by 10 to the power of minus 8, which is 10 to the power of 8. What does it mean? Within 1 centimeter of nickel crystal, we can get 10 to the order of 10 to the power of 8 slits. And this is very huge when large number of slits are available within a nickel crystal. So we can use this nickel crystal as a grating. And this is experimental arrangement taken by Davisson and Germer. See, first we'll try to identify the three primary components. So this is source, electron gun is the source, and this is grating. I mean nickel crystal is grating. And the third one, this is Faraday cylinder to collect the diffracted electron beam. Now we'll see that individually. Now this electron gun, I mean that electrons will be liberated from hot tungsten filament. I mean, in order to make that tungsten filament with high temperature, we need to apply a potential difference of P. And in this experiment, they applied with a 54-volt potential difference. So what does it mean? By applying a 54-volt potential difference across this tungsten filament, so it will get heated. That heated tungsten filament will liberate the electrons in all possible directions. Of course, electrons will be liberated, emitted in all possible directions. But for diffraction experiment, it is better to be a fine beam of electron. I mean, the direction of all the electrons must be in same. Then the diffraction phenomena will be appears to be very good. So, in order to make a fine beam of electron, so we are placing collimators. By some means, we are placing a collimator, so that the high angled electrons will be stopped at these collimators only. A fine beam of electron will be liberated from the source. Now this electron beam, a fine beam of electron beam, is allowed to incident on the grating. I mean, allowed to incident on the nickel crystal, right, which consists of large number of slit. So this empty region is slit, right? So because of this grating, now the direction of electron will be changed. I mean that electrons will be spreaded in all possible directions. Now we need to collect all the diffracted electron beam by some means. Here we are collecting that diffracted beam by Faraday's cylinder, right? But we need to collect that in all possible directions. So now we'll give a facility that this Faraday cylinder can be rotated with all possible angles. Of course, it will rotate about an axis which is passing through the center of the nickel crystal. So it can rotate with about an axis passing through the nickel crystal. So we'll move this Faraday cylinder with any angle. And of course, we'll measure that intensity of diffracted electron beam just by connecting a ammeter that will measure in terms of current. So if you get more current at this position, is nothing but the intensity of diffracted electron beam is more. I mean, more number of electrons are deviated in this path. If current is less, is nothing but the number of diffracted electrons are less in the direction. So we'll measure that intensity of diffracted electrons through this electrometer, the reading through this electrometer. So this is mechanism, and we'll do the analysis. So for 54 volt, and that Faraday cylinder is rotated in all possible directions. So in that process, more number of electrons are diffracted if it is with an angle of 50 degree. And see here we can show that in diagram. So that electrons are incident on the nickel crystal. So after incident on the nickel crystal, because of this grating, they are deviated in this direction. They are deviated in this direction. So this is angle of deviation. And this angle of deviation, for this angle of deviation, more number of electrons are coming in this direction. See, the electron may be deviated in this direction also. In this direction also. But pronounced diffraction occurred with angle of deviation what 50 degree. Right, so if this is the plane we are considering, and this will normal drawn to the plane with respect to normal drawn to the plane, it will be pi by 2. You can divide that into pi by 2 and pi by 2. So, but this pi is equal to 50 degrees the angle of deviation, but angle of diffraction will be, here it is, 90 minus pi by 2 is 65. I mean, if you remember the Black's law, let be these are atomic planes, and this is normal drawn to the atomic planes. Let be this is incident wave and this is diffracted wave. is incident with an angle of theta and diffracted with an angle of theta. Here that pi equal to 50 degree, this is angle between these two lines. This is 50 degree. But angle of diffraction is always measured with respect to that atomic plane. So if it is 50, so this is 25. Right now this total angle is 90 because this is normal. 90 minus 25 is the angle of diffraction. Now we'll apply the Bragg's equation. Which is the condition for maximum intensity of light. 2d sine theta is equal to n lambda, where this n is equal to order of diffraction. Like this is first order, this is second order, this is third order. Different directions are the orders. So first, we are doing that for first order diffraction. And d is the interplanar spacing. We are taking nickel crystal. For nickel crystal, that interplanar spacing is order of 0.909 into 10 to the power of minus 10 meter. And we'll substitute all these in this Bragg's equation. I mean 2 into 0.909 into 10 to the power of minus 10 meter and sine 65 lambda. The final result, wavelength of that electron, is coming to be experimental value 1.64 angstrom. It is accelerated by 50 voltage. And we'll calculate the theoretical value, which is suggested by de-Broglie. So we already written this equation. For charged particle, lambda is 12.27 by under root b angstrom. Under root b angstrom. Here the potential difference we applied is 50 volt, 54 volts. Potential difference we applied is 54 volt. So for 54 volt, it is coming to be 1.668 angstrom. So now if you compare both experimental result and theoretical result, both are very nearby. So experimental and theoretical results are matching. Is nothing but whatever the hypothesis suggested by de-Broglie, matter will exhibit the wave nature. It is true, and it is experimentally confirmed with this experiment. Right? Till now, quantum mechanics, we adopted a new concept from de Broglie hypothesis. We adopted a new concept, that is, matter is exhibiting wave nature. Right? Wave is nothing but is a disturbance in a medium. Disturbance in a medium. Right? This is better to prolong. Let be an electron is moving. As per classical mechanics, this should be the path of the electron, the linear path. But as per quantum mechanics, it is exhibiting the wave nature. It is a region of spreading. So if it is exhibiting the wave nature, the one problem is we cannot identify the position, or we cannot locate the particle position of the particle at a particular instant of time, because at that particular instant of time the electron, the particle can be located, can be in anywhere in this region. That is mean by uncertainty. We cannot give the exact. And if you see a little bit analysis, if that electron is exhibiting this type of wave, see, this is very narrow wave, narrow spreading, disturbance in very narrow, small region. There you can calculate, locate the particle position with less uncertainty. You can give more accurately. But here, to calculate the momentum of that particle at that position will be less accurate. That error will be more. Uncertainty will be more. This delta represents uncertainty. Uncertainty is more. If that same particle is spreaded over a long region, see, this delta is more here. Locate the position of the particle is more. Uncertainty is more. but where you can give the value of momentum little bit more accurate. I mean, uncertainty is less. I mean, I'll try to give one example to understand the concept of uncertainty. Like now, let be in a class. Let be in a class. Some student is written exam for 100 marks, and we just for the sake of interest, we just asked him how many marks that you may get. If you say, if that student say, I'll get some 70 marks, you'll see that later on whether you'll get 70 or not. You'll see that later. It's not an issue right now. He said that I will get some 70 marks, so he's confident. I mean, he's certain. He's giving exact value. I will get 70 marks. But if he say some 65 to 70 marks, 65 to 75 marks, so here that uncertainty is there. With uncertainty of what? 10. So it's not giving the exact marks, but it is giving a range of marks. If he says 65 to 70, here also uncertainty is there, but uncertainty is 5. I mean, compared to this is more accurate. If you compare both these, this is little bit more accurate because uncertainty is less. Similarly, similarly, um, if the electron, I mean, particle is exhibiting wave nature, I mean, it is spreading in a region. So we cannot give the position of the particle where it will be. It is not accurate. Definitely, it is having some uncertainty. Then, if it raises uncertainty, then what that Heisenberg's principle is. So this is generalized definition. It is impossible to specify precisely and simultaneously. We cannot separate it both. Precisely in the sense accurate. Precisely in the sense accurate. So it is impossible to specify precisely and simultaneously the values of both the members of particular pair, both the members of particular pair of physical variables that describe the behavior of an atomic system. I mean, it means so number of physical variables are there to define or to be explain the behavior in atomic system. Out of all the physical variables, a special set of variables are there. Special set of pair variables are there, like position and momentum. Now, your interest is to measure the position and momentum of that particle simultaneously, right? You are interested to measure the position and momentum of the particle simultaneously. So it is not meaning that you cannot measure it. You can measure it. You can measure it simultaneously. Impossible in the sense, not, it is not possible to not possible to measure simultaneously. I mean, we need to consider both. So you can measure them, but it will give some uncertain value. Like if value may be like from 65 to 75 somewhere. You can estimate the value, but you cannot give the exact value. So this occurs for a particular pair of variables. One set of variables, this problem will for position and momentum, and even some other variables are also there, like energy and time. Energy and time. So these two members also you can measure that simultaneously, but when you are measuring that simultaneously, the result will be not exact value. It is having some uncertain value. And another example such pair was angular momentum and angular position, right? But how much that uncertainty will be? Like here, that uncertainty is 10. Here, that uncertainty is 5. Similarly, for this particular pair of variables, if you measure that simultaneously, the minimum amount of uncertainty will be h by 4 pi. It may be greater than that of, maybe greater than also, but minimum will be h by 4 pi. So we cannot give the accurate values for that for a particular pair of variables. And this uncertainty principle simply you can explain through mathematically also. That particular pair of variables not commute each other. They will not commute each other. Commute in the sense, I'll take some A and B. So as per commutative law, if this is commutative law of A and B, AB minus BA should be 0. I mean like 2, 3. If you do the commutative law for 2 and 3, 2 into 3 minus 3 into 2 will be 0. If it is 0, they will commute. But for this particular pair of variables, if you calculate the commutator, I mean position and momentum, this x into p minus p into x will not be 0. They will not commute each other. So if they will not 0, there should be some value, right? How much that value is? Minimum h by 4 pi, maybe greater than, but it is minimum h by 4 pi. So they will not commute each other. So that is the idea of uncertainty principle. Now we'll see the next segment, the mathematical tool to solve the physical problems through quantum mechanics. And that mathematical tool is Schrodinger's time-independent wave equation, or you can say equation of motion in quantum mechanics. Equation of motion. Equation of motion of quantum mechanics. See, we are also having equations of motion in classical mechanics also. In kinetics, F equal to ma is the equation of motion. In kinematics, there are four equations. Are there? V is equal to u plus at. S is ut plus half at square, right? And v square minus and so on. V square minus u square is 2as. Sn is equal to u plus n minus half of a. All there are equations of motion in kinematics. And what is the purpose of all these in irrespective of branch, irrespective of branch? What is the purpose of branch of physics, irrespective of branch of physics? What is the purpose of equation of motion? The title itself is saying. With the help of that equation, we can explain the motion of the particle. I mean, explain in the sense how its position is changing. What is its velocity with respect to time? What is its kinetic energy and potential energy? All these quantities can be calculated with the help of this equation of motion. And of course, mathematically it should be in second order differential equation form. See here that A is d2x by dt square. So mathematically it will be a second order differential equation form. So this is that equation of motion in quantum mechanics. And if you see this particular function, we will see that what does it mean by psi. Generally it is called as wave function. Wave function depends on both time as well as the wave function depends on position. Position coordinates x, y, z. But for the time being, we are trying to give the equation only time independent. This is in general. I mean, we need to remove this time dependency term d2 psi by dt square, because the wave function depends on time. We need to remove this particular left hand side of the equation. That is our aim in this derivation. So for that, what we'll do, we will do some mathematical operations, series of mathematical operations. The whole purpose is make this as time independent, right? And just here, this is generalized equation, and where this v square dou 2 psi by dou x square plus dou 2 psi by dou y square dou 2 psi by dou z square is del square psi. Here, the del square is Laplacian operator. And generally, it is defined like it is dot product of vector product, sorry, dot product of del. I mean, del is a vector operator which is I dou by dou x plus j dou by dou y plus k dou by dou z dot again I dou by dou x plus j dou by dou y and k cap dou by dou z. So if you do the dot product of two vectors, only like unit vectors dot product is 1. The remaining unlike unit vectors dot product is 0. So the result will be I dou by dou x, I dou by dou x dot product will be 1. J dou by dou y and j dou by dou y dot product is 1. K dou by dou z and k dou by dou z is 1. The remaining other all combinations will be 0. So the result will dou square psi by dou x square, dou square psi by dou y square, dou square psi by dou z square. This is Laplacian operator. And of course, this v. V is velocity of wave. Right? So if this is the second order differential equation format, then the solution will take in this form. Psi of x, y, z, t. I mean, the wave function depends on both position as well as time. That psi of x, y, z, comma t will be equal to what? Psi naught of x, y, z. I mean, just see here, you are separating the position dependency and time dependency. Psi naught of x, y, z and e to the power of minus I omega t. Right? Or in three dimensions, simply you can write instead of x comma y comma z, it simply you can write r. So psi of r comma t is psi naught of r e to the power of minus omega t. So from now onwards, we'll take some liberty. I mean, instead of psi r comma t, I mean, instead of writing entire term repeatedly, psi of r comma t will represent it as psi. And psi naught of r is represented as psi naught. This is just for the sake of convenience. And we'll follow this throughout the derivation. So now this is the general solution it will take in this form. Now, in order to remove the time dependency, we'll do one thing. We'll differentiate this two times. We'll differentiate this two times and we'll substitute in this equation, in that above equation 1. Right? I mean, I mean, one second. Sorry. Yeah, we define this psi as psi naught of e to the power of minus I omega t. So it's first derivative dou psi by dou t. The psi naught is constant, so as it is e to the power of minus I omega t differentiation is e to the power of minus omega t, and this is minus I omega. And if you differentiate again, dou 2 psi by dou t square is minus as it is, right? I omega psi naught e to the power of minus I omega t differentiation is e to the power of minus I omega t, and minus I omega t differentiation is minus I omega. So here the minus into minus will be plus. I into I is I square, which will be minus omega square and sine out of this. So it's second derivative minus omega square sine out of e to the power of minus omega t. But you can write this entire term as what? Sine. Right? I mean, the second derivative, I mean, dou 2 psi by dou t square is minus omega square sine that we obtain. So we will substitute this in equation 1. So instead of dou 2 psi by dou t square, we will write minus omega square psi, and right hand side will be as it is. And we'll write this at one side. See, for equation both sides will be there. We'll write that at one side. So this is as it is. Dou 2 psi by dou x square plus dou 2 psi by dou y square plus dou 2 psi by dou z square. and you are dividing with v square also. So omega square by v square psi is 0. Now see, there is a no time dependency in this equation. I mean, there is no dou psi by dou t. Or in simple form, you can write del square psi. I mean, this entire can be written as del square psi plus omega square by v square psi is 0. Now it is time dependent equation, of course, but it is better to write in energy form so that you can solve the physical problems with a little bit easily. So we achieved the time independent wave equation, but it's better to write in which form? Energy. So whatever the mathematical operations or I mean, equation substitutions are there, the final aim is to write in the form of energy. So for that, the first step, we'll take the relation between omega and nu. I mean, angular frequency and linear frequency. So the relation is omega is equal to 2 pi nu, right? Then again this nu is equal to v by lambda. The frequency nu is equal to v by lambda. So this omega can be written as what? Omega equal to 2 pi. Instead of nu, we'll write v by lambda. So what is the result? Omega by v. I'm just you are writing this velocity denominator of this omega. So omega by v is 2 pi by lambda. Then its square will be 4 pi square lambda square. So we'll substitute in this equation 4. This equation 4. I mean, just see, this is as it is. Instead of omega square by v square, it is 4 pi square by lambda square psi is 0. Right, in Laplace and operator, this is the form. Now the second step, apply the de-Broglie wavelength. From de-Broglie wavelength, lambda is equal to what? H by mv. Then lambda square will be equal to what? H square by m square v square. Then reciprocal of this will be, I mean, 1 by lambda square is equal to m square v square by h square. So now we can apply here. I mean, apply this 1 by lambda square in equation 5. So the equation will be del square psi plus 4 pi square by h square m square v square psi is 0. So the third step. See, till now we didn't got that equation in terms of energy. Now you can turn this into in terms of equation energy with this last step. So here the total energy is E, which is the sum of both kinetic and potential. I mean, this total energy is kinetic and potential V. And then this kinetic energy is equal to what? Total minus potential. So come here. The kinetic energy is equal to total minus potential. Right? Multiply on both sides with mass. Multiply with both sides with mass and write the denominator this 2 to right side. The result will be m square v square is 2m of total energy minus potential. Now do this equation 7 in equation 6. So that del square psi as it is and 4 pi square by h square as it is. Instead of this m square v square, it is 2m of total minus potential psi equal to 0. The final equation will be this is del square psi plus 8 pi square m by h square of e minus v psi of psi equal to 0. Now this is time independent Schrodinger wave equation in terms of energies. Now this is better way to use to solve the physical problems. Let be if any particle is not having any potential. I mean the particle is not influenced by any potential energy. It is free from potential energy. Then we'll substitute this v as 0. So this is for free particle. This equation is for free particle. Now we will see the physical significance of wave function. So the wave function psi is not having any direct physical significance, but it is square square of the magnitude of wave function is having a significance, and is generally used. I mean, square of the magnitude of a square of the wave function uh, is evaluated in a particular region to measure the probability of finding the particle in a region. I mean, we already said Eisenberg's uncertainty principle raises the concept of uncertainty. So we cannot locate the particle exactly at a particular instant of time, but it will give some range of value, right? I mean, if we can explain that through diagram, like let be this is wave exhibited by the particle. Now within this region, now you are selecting a small segment dv, a small segment dv. So the particle can be right from here to this end. So then what is the probability of finding the particle in this selected region, that you can evaluate by just squaring the magnitude of this wave function. I mean, just let be psi is the wave function, and its complex conjugate is let be psi star, will give you magnitude of psi square. So we'll say this is modular psi square as a probability density of the particle, right? Probability density of the particle. And if it is in three dimension, if you are measuring the three dimension, dv, it can be written as dx, dy, dz, right? So if you see the generalized equation, now you are selecting a small segment with the length, with the length, with the length as the previous diagram I showed. I just drawn that. Now this is dx, dy, and dz. So first we will calculate the probability density in this small volume, then integrate with the, I mean, x, y, and z direction. So that will give the probability of finding the particle. So in general, we'll take that limits from where to where we are finding that. In general, it is minus infinite to plus infinite. This is generalized limits. It is not always minus infinite to plus infinite. Depending on the physical problem, we will change the limits. If you are calculating this probability density, even you can calculate that along a particular direction also. So there you will get a single integral modulus psi square, let be the direction is dx, is equal to 1. So that 1 will depends on what the limits you are defining. Now we'll take the applications of Schrodinger's time independent wave equation. One of the physical problem is particle trapped in a one-dimensional potential box, or you can say particle in an infinite potential well. So for any physical problem, first we need to divide that, as per physical problems, we need to divide that into some regions. See, now first we draw the diagram, I mean potential behavior as per the physical problem. Now these are the boundaries. These are the boundaries for electron. What does it mean? That electron is moving within this boundary and not even at the boundary. This is moving only within the boundary. And the boundary height is infinite. I mean infinite, like infinite well. And the length of that boundary is right from x equal to 0 to x equal to L. So now based on this data, now we can divide that into two regions, region 1 and this is region 2. This is region 3. But however, in region 2 and region 3, the potential is same. V is 0. V is 0. So we'll call them as same region 2 in which potential is 0. Right? And now we'll define that in region 1, right? And what that region 1 is, the position of the particle, I mean electron, is in between 0 to L, in between 0 to L. Here the potential is 0, right? And region 2, sorry, here it is infinite. Here it is infinite. Region 2. So region 2 is x is less than or equal to 0, and even x is greater than or equal to L, both sides. Here the potential is infinite. Now we need to apply the Schrodinger's time independent wave equation, but is it we need to apply in both the regions? No. So we need to apply Schrodinger's time independent wave equation only in which region that particle is moving. Now, as per our discussion, the particle is moving only within this region 1. So no need to apply Schrodinger time independent wave equation in second region, right? And if you apply that in one dimension, the Schrodinger time independent wave equation is dou 2 psi by dou x square plus 8 pi square m by h square e minus b of psi is equal to 0. In region 1, the potential on the particle is 0. So now it will take this one, dou 2 psi by dou x square plus 8 pi square m by h square e psi is 0. And for the sake of convenience, because all these are constants, so we'll take a common constant like k square. So that it will becomes a standard second order differential equation. I mean that standard form of second order differential equation is dou 2 psi by dou x square plus k square psi is 0. Now, if this is the form of a second order differential equation, it will take, I mean, the solution will take in this form. I mean, psi of x will be a sine of kx plus b cos of kx. And in this, a and b are arbitrary constant. We don't know that value right now. So that's why, I mean, there will be some constant, but we know that exact value. That's why we are saying arbitrary constant. But we need to find them. To make that general solution as exact solution, we need to find the values of a, b value, and even k value also, so that the solution will becomes exact solution. And in order to find the this arbitrary constants value, we'll apply the boundary conditions. I mean here that boundaries for particle is at x equal to 0 and at x equal to L, because the particle is moving within the boundary, within these two boundaries. So the conditions at the boundary, first we'll take the first boundary at x equal to 0, and we are saying that the particle is even not moving at the boundary. So if there is not moving at the boundary, there will be no wave. Is nothing but no wave. And as per we discussed the characteristic of matter waves, if particle is moving, then only we can define its wave nature. If wave nature is there, then only we can write the wave function. So if particle is not moving at the boundary, so there will be no wave function. So psi of x will be equal to what? 0. Now we'll apply this condition in a general solution. The psi of x equal to 0, a sine of 0 plus b cos 0. Of course, cos 0 is equal to 1. Cos 0 equal to 1. Sine 0 is 0. The final result will be what? B is equal to 0. So now the general solution will change to psi of x is equal to a sine of kx. Now we'll apply the second boundary condition. Second boundary condition, which is x equal to L. And at this boundary also the particle is not moving. So here also the wave function will be equal to what? 0. I mean psi of L is equal to psi of L is equal to 0. And if we apply that, instead of x, here it will be L. The psi of L is 0. A sine KL. So that A cannot be 0. Amplitude cannot be 0. So that's why definitely sine KL must be equal to 0. And the sine function will be 0 for every n pi. For every n pi. So, I mean, sine 0 is 0, sine 0 is 0, sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, and so on. But here, we are not taking the n equal to 0 because for n equal to 0, k will be 0 and energy will be 0 and psi wave function will also be 0. I mean, everywhere in the box. So that is meaningless. That sense meaningless. So that's why we will not take n as n equal to 0. It starts from pi. So this KL, I mean, we can write this equation like this. Sine KL is equal to sine n pi. That 0 can be written as sine n pi, where n starts from where 1, 2, 3, and so on. So that if both are equal, now we can write KL as equal to n pi. So that K is equal to n pi by L. Now this equation 5 will change to what? Psi of x is equal to a sine of n pi by L x. Right, but just see the equation 2 where we consider this as 8 pi square m by h square e we consider it as k square. This is equation 2. And from equation 6 where this we got k is equal to what? N pi by L. So that k square will be n square pi square by L square. So both are equal to what? K square. So equate them. If you equate them, then the pi square on both sides will be cancelled, and the final result will be E is equal to n square h square by ml square. Or you can say it is En. So different possible energies are obtained. I mean, if you substitute n equal to 1, that is E1, h square by 8 ml square, we will say this is ground state, minimum energy ground state. And remaining all are excited state. And n equal to 2 is the first excited state, or you can say second energy level. It will be 4 times to the ground state energy. And second excited state, which is third energy level, E3, 9 times to the ground state. And what does it mean? With this calculation, we can observe that if particle is moving in infinite potential well, that particle will not move with all possible energies. The particle will move only with certain energies, and that energies are integral of h square by 8 ml square. I mean n square times to the h square by 8 ml square. Other than sorry, other than these energies, the particle will not move. I mean either it move by h square by 8 ml square energy, or 4 times to the h square by 8 ml square, or 9 times to the h square by 8 ml square. What does it mean? That energy of the particle is quantized. Energy of the particle is quantized. I mean it is discrete in nature. All energies are not possible, only certain energies are possible. But till now we calculated the A value, I mean B as 0, b as 0, and k as n pi by l, but we didn't calculated the a value. So in order to find the a value, we'll apply normalization condition. Normalization condition. I mean, which is probability density. Probability density. Right. So here we ended previous slide. This wave function psi n of x is equal to a sine of n pi by l x. And now we'll take its complex conjugate and we'll do the product and we'll integrate that in between 0 to l. See, in general, we written previous slide that is a minus infinite to infinite. But now we have a clear boundaries because the particle is in between 0 to L. So accordingly, we change the limits from 0 to L. So its probability density 0 to L psi n of x psi n of dx whole square is equal to 1. What does it mean? That particle will definitely existed between 0 to L limits because the maximum value of probability is 1. What does it mean? Definitely the particle will exist in between 0 to L. And if you square it, so of course a is common, so a square we can write out of the integral, so 0 to L sine square of n pi by L x dx equal to 1. Now but it is with higher order, power is higher, I mean it is little bit difficult to solve this integral. So that's why we will take the trigonometric identity. Sine square theta is equal to 1 minus cos 2 theta by 2. That here, yeah, instead of theta n pi by Lx. So accordingly, just apply this trigonometric identity for this equation. So that a square as it is 1 minus, I mean integral 0 to L 1 minus cos 2 n pi by L of x over by 2 dx equal to 1. And here this 2 is also constant. So a square by 2 0 to L 1 minus cos 2 n pi by L x dx equal to 1. Now distribute this integral for both the terms. I mean a square by 2 integration of 1 is x minus integration of cos is sine 2 n pi x by L by, and for this I mean cos n theta, if it is n theta then sine n theta by L. Here instead of n, this 2 n pi by L is there. But however, if you apply the limits, this total term will become 0. Mathematically, this total term will become 0. So now we need to apply the limits only for for x 0 to L. So if you apply that, a square by 2 L minus 0 equal to 1. So that a square by 2 L equal to 1. The final value of a will be under root 2 by L. So the final wave function is, after doing all the mathematical operations, the final wave function psi n of x is under root 2 by L sine n pi by L x. Now, if we draw the wave function and its probability density graphs, see there, this is first energy level. I mean, if you apply that, psi 1 of x is under root 2 by L sine, instead of n, we need to write 1 because it is for ground state. So remaining will be pi by L x. And if you see, this is sine behavior and the maximum angle here it is pi. So that's why we got only half of the sine wave. If it is for second energy level, I mean first excited state, under root 2 by L sine 2 pi by 2 pi by L x. So maximum angle here it is 2 pi. I mean, that's why um, we got a complete sine wave. And here it is 3 pi by L. I mean 1.5 sine wave. And if you square that, however we are taking this as modulus, so irrespective of the wave function whether it is plus or minus, the probability density will be always positive. So that's why we got only positive hums. So two hums are there, but for density it will be two positive humps. Three humps are there, three at positive. So what does it mean? Just see here. If that particle is moving with E1, I mean h square by 8 ml square, the most probable location to find the particle is somewhere here, which is at L by 2. At exactly half of the box, more probability is there to locate the particle. If that particle is moving with E2, I mean 4 times to the E1. So two most probable locations are there. There you can find the particle more with most probable value, which is L by 4 and 3L by 4. And if it is moving with E3, I mean 9 times to the ground state energy with higher energy comparatively. So three most probable locations are there, right? L by 6, 3L by 6, 5L by 6. And if you observe, this is more or less similar, not exactly same, but more or less similar to that known data for us. The definition of orbital is the most probable location to find the electron. Most probable location to find the electron. So just see there. Just try to apply this. If it is in ground state, I mean first orbit. Let me this is nucleus. Let me this is nucleus, and this is first orbit. N equal to 1, n equal to 2, and n equal to 3. I'm just giving the comparison. Both are not exactly equal. If n equal to 1, the most probable location is only one, which is s orbital. If n equal to 2, the most probable locations are 2, s orbital as well as p orbital. If n equal to 3, most probable locations are 3, s, p, d, and so on. Right? That is meant by the most probable locations to find an electron. Now we'll see the second application, which is tunneling effect. The basic idea of tunneling effect is, let be energy of the particle is E, but now it is encountered an obstacle which is having a potential more than the energy of the particle. Now see, diagrammatically you can represent here, right? So this is the obstacle boundary. The height of the boundary is V. Now see the energy of the particle. It is less than height of the boundary. What does it mean? E is less than V. So total energy of the particle is less than potential encountered by the particle. So under such condition, um, classical mechanics is saying that the particle cannot penetrate through this barrier. So it will stop at the barrier only. But if you see one example like alpha particle emission from the nucleus, alpha particle emission from the nucleus. So generally energy of the particle, alpha particle, emitted alpha particle is order of 5 mega electron volt. And potential offered by the nucleus, this boundary is order of 100 mega electron volt. So if this is the case, what does it mean? E is much less than V. So if it is the case that as per classical mechanics, this alpha should not penetrate through this barrier. It should be within this nucleus only. But practical it is coming out. Even though total energy of the particle is less than potential, practically that alpha particle is coming from the nucleus. So this is one more example where classical mechanics is failed to explain the penetration of alpha particle from the nucleus. But quantum mechanics is successfully explained. So there is a probability of emission of particle even though total energy is much less than potential. And further, the mathematical tool we applied is again the Schrodinger's time independent wave equation. So just we are taking only conclusion. We are not going with the entire derivation, right? So the transition probability of is probability density of transmitted wave. I mean this one. This is psi 3 before appearing to this barrier psi 1, Within the barrier it is psi 2, and after penetration the wave function is psi 3. So this is transition. Psi 3 is the transition, psi 1 is incident. So the probability density of transmitted wave by probability density of, sorry, incident wave. So if let me, if particle is not coming out of the barrier, this transition probability should be zero. If it is zero, the particle definitely will not penetrate through this barrier. And if this equation is applied to the alpha particle from the nucleus, the transition probability is coming to be this much: 16 total energy by potential energy 1 minus E by V of exponential minus 12 under root pi square mb minus E by h. I mean, if this value is zero, the particle will not come out. If it is non-zero, definitely it will come out from the barrier. And this is non-zero for alpha particle coming from the nucleus. So transition probability is approximately 0.004. Right? I mean, for every thousand times, I mean, this alpha particle in collision with the boundary of the nucleus, for every thousand times, there may be a chance of 4 times it will penetrate through the barrier. And one more example for such tunneling effect is the electronic device, which is tunnel diode. Right, this tunnel diode is, I mean, when the junction forms, PN junction forms, after formation of PN junction, there is no further movement of charges through this PN junction barrier, right? And it is possible just by applying the higher amount of potential, still it can penetrate through the barrier. This is one more example for a tunneling effect. Thank you.